All right, welcome everyone to the Unitronics webinar on PID and auto tuning. My name is Daniel Logie. I'm an applications engineer here at Unitronics. I'm accompanied today by my colleagues Alex and Mike. If you have any questions during the webinar, you can enter them into the questions and/or chat box. Mike and Alex would be happy to answer any and all questions you do have. We'll also be holding a short questions and answers session at the end of the webinar. So if you'd like to hold your question to the end, you can feel free to do that as well. All right, so let's begin. Again, we're covering PID and auto tuning today. PID is a form of system control. I'm going to start by providing a few sample systems that may be using PID control. The heating or warming of a room, cruise control in your vehicle, a oven, a piston on a load cell, dampers that are regulating airflow, various types of HVAC systems, and a proportional valve with a flow meter. Now, any one of these systems may be running PID controls. All of the systems have two things in common. They have some type of system feedback, and they also have some type of control. For example, the room heating. The feedback to the system would be the current temperature in the room. The control aspect would be the heater that is providing the heat to the room. For the rest of the presentation here, I'll be using this room heating example. Now, before I get into PID, I would like to explain a little bit about an alternative type of control, which is on-off control. When I say on-off, I mean that this type of control turns on and off an output 0 or 100%. As an example, if you're staying in a hotel room and your hotel room is warm, you can walk over to the air conditioner and turn on the air conditioner. Eventually the room is going to cool and you'll no longer need the air conditioner, so you can turn it off. Over time, the room will then warm up and you will become warm again, and then the air conditioner will be again needed. This type of system is an on-off control. The output is either on or off. The pros of this type of system is that it is easy to understand and easy to perform. This type of control we can even do in ladder logic. The cons of this system is that it is not precise. If you remember the example I gave a minute ago with the air conditioner, the temperature in the room is going up and down in a sort of wave pattern. The temperature goes up, turn on the air conditioner, and it goes down. This is not ideal for most systems, this type of wave. So before I move into the PID explanation, I'd like to get familiar with a little bit of terminology. First, the process value. This is the current input of the PID. Next is the set point. This is the target for the process value. This is user defined. And finally, we have our control value, which is the output of the PID. With our room temperature example, the process value would be the current temperature of the room. The set point would be the temperature that we would like the room to be at, and the control value would be how hard the heater is currently working. So now we'll discuss a little bit about PID. What is PID? A PID function uses system feedback to continuously control a dynamic process. Now you'll see in the diagram below, we have a set point, which is our target value. The set point is then compared to the process value, which is our input. Comparing these two, we get some sort of error, which is provided to the PID. The PID then makes its calculations based on this error and provides an output. So let's start with an example. Currently in my office, it's about 75 degrees Fahrenheit. I apologize. Currently, I would like my office to be about 75 degrees Fahrenheit, which is my set point. The current temperature in the office is 70 degrees Fahrenheit. When I compare my set point to my process value, I get an error of 5 degrees. The current temperature is 5 degrees below my ideal temperature, my set point. This error will be provided to the PID to calculate an output between 0 and 100%. Now the output is based on your system. For example, if I'm attempting to control the temperature in an entire office building using a heater, this might take more output or more effort than if I'm attempting to control the temperature in a single room using the same heater. So the PID is intuitive, it's adaptive, and it learns your system. What exactly does PID stand for? It stands for proportional, integral, and derivative control. These three types of control account for our control value, which is our output. The total control value is equal to the control value from the proportional plus the control value from the integral plus the control value from the derivative. These three combined make up the total control value. You see in our diagram below, this is the ideal pattern for a PID loop. Our process value begins below the set point. It approaches the set point. It finally meets the set point, and the process value then remains at the set point for as long as the user defines. Now the first type of control I'm going to discuss is proportional control. Now when we're dealing with proportional control, a band or range around the set point is defined. This is called the proportional band. The proportional band is a percentage of the process value range. In my example below, my process value is a thermocouple with a range 0 to 100 degrees Fahrenheit. In this example, the proportional band is set to 10% of that range. So 10% of the range 0 to 100 is 10. 10 is then added and subtracted to our set point of 50 to get our proportional band range, which is from 40 degrees Fahrenheit to 60 degrees Fahrenheit, as shown in the diagram. Now when the process value is at the lower end of the proportional band, the output is 100%. When my process value is currently at the set point, the control value or output will be 0%. When the process value is within this range, the control value is directly proportional to the size of the error. So if our process value is currently at 40 degrees, the output will be 100. And as we slowly approach the set point, the output or control value will drop until we finally reach the 50 degrees, when our control value will be 0. If we are outside of the proportional band, the process value is outside of the proportional band, then the output will be 100%, and there will be no PID action, meaning the PID will not calculate. We are not close enough to the set point for the PID to work, so the output is 100% until we reach the proportional band. Now the example that I just explained is for a heating application. Our process value begins below the set point, and our goal is to increase the process value to the set point. The same rules apply for a cooling application. If our process value begins above the set point, let's say at 100 degrees, and our goal is to cool to 50 degrees, the same rules of proportional band apply. When outside the range, the output will be 100%. Once we reach 60 degrees, the output will then be directly proportional to the error. Now when we're dealing with proportional control, the control value will be equal to the control value proportional. You see in my graph to the right, the set point is indicated by the blue line, the process value is indicated by the red line, and the control value is indicated by the green line, as well as the black line. Now you'll see as the proportional value approaches the set point, the control value decreases. Some pros to proportional control only is that it's simple and easy to implement. The cons is that our process value will never reach the set point. As the process value approaches the set point, the output will become lower and lower. The control value will become lower and lower. And we will never quite reach the set point. Integral control compensates for the proportional control shortcomings. Now what do I mean by this? I mean that the integral control is going to look into the future, and it's going to calculate based on the current curve whether or not our process value will reach the set point. If the process value will not reach the set point, then integral control will be added to proportional control to create our control value. So it's going to add output to what was already calculated using proportional control. The integral time is set in the PID configuration, and it is the ideal amount of time that we would like the process value to reach the set point. And you see finally my control value in this case is equal to the control value proportional plus the control value integral. Now we will see the graph below. The blue line again signifies the set point. The red line signifies the process value. And the green line signifies the control value. Now you'll see a new line, which is pink near the bottom, and this is the control value of the integral. Now as the process value approaches the set point, the integral calculations are going to realize that we are never going to quite make the set point using proportional only. So the integral calculation is going to add to the control value. And you see in this example our process value reaches the set point and even passes the set point for a brief moment. Before I move on, I'd like to note that the red line, signifying the process value, is a little bit more bumpy, or wavy, if you will, than the straight proportional control. This is because of the aggressiveness of the integral control. It causes the path of the process value to be a little bit more bumpy. It's a little bit bumpier of a road to the set point. I'd also like to note that when the process value is equal to the set point, circled in blue, the control value is equal to the control value of the integral. The control value proportional no longer plays any effect in the output because we are at the set point. So the control value, when we reach the set point, is strictly driven by the integral calculations. Next, we'll discuss our final topic, which is derivative control. Now, derivative control compensates for the integral shortcomings. And again, we remember that integral control causes a bumpy road to the set point. The derivative control is going to look into the past, and it's going to see the previous path of the process value. And the derivative control is going to try and keep this process value on its current path. So it's going to add and subtract from the control value in an attempt to keep the process value smooth. So derivative control essentially smooths out the curve. Next, I'll move on to my control options. Proportional control is responsible for the majority of the control value, responsible for the majority of the output. Therefore, proportional control is needed. Our options can be proportional control only. We discussed this already. This type of control will never reach the set point. The process value will never equal the set point. We can have proportional and integral control only. In this case, we will reach the set point. However, the process value path might not be as smooth as we would like it. We can have proportional and derivative control only. In this case, the process value will never quite reach the set point. However, the curve will be smooth. And we can have full PID control. Next, I'd like to discuss a little bit about PID control in vision controllers. PID control is done using function blocks, and we're going to get into this in a moment. Many independent PID loops can be controlled simultaneously. In the enhanced series controllers, 24 total loops can run at one time. In the standard series, 12 loops can run at one time. And the Jazz and M91 can also support up to 4 loops. So as I mentioned, PID in vision controllers use function blocks. The most important function block is the PID configuration. The PID configuration must be run one time. We recommend that the PID configuration run in the main routine off of the power-up bit SB2, as shown below. Now let's take a look into the PID configuration function block. I'm going to discuss this a little bit more in depth in a moment. However, you'll see the first variable is our set point for the PID. Our second variable is our process value. In this example here, it's a PT100, or temperature measurement. We then have our proportional band, integral time, and derivative time, which are our controls. We discussed these earlier in the presentation. The good news is that these 3 parameters, or variables, will be found using our Autotune process. The next variable is a sample time. This is how often the controller recalculates. The units are 10 milliseconds. We then have our action, or direction, which is reverse or direct, heating or cooling. Essentially, it's asking us, is our process value starting above or below the set point? If our process value is starting below the set point, we will be using heating. If our process value is starting above the set point, we will be using cooling. We then have our input range, which is our process value, low and high limit. In this case, the input range would be the high and low limits for our PT100. You can see we have set 0 to 1000. Our next two parameters are our output range, our control value low and high limit. We have set 0 to 1000 as this range. This represents 0 to 100% with a 1 decimal offset. Once we have this 0 to 100%, we can apply this to any output we desire. All we must perform is a linearization. So if we have a 10-bit, 12-bit, or 16-bit analog output, we can linearize and make our adjustment. Right below our output range is our control value. Again, this is the output of the PID. It's going to be between 0 and 100%, or 0 and 1000 rather, 0 and 100% with a 1 decimal offset. Our next variable is our PID status. This will tell us if there is anything wrong with the PID system. Finally, we have PID Autotune parameters. This is a group of 32 MIs, and these MIs are used for calculations of the controller during Autotune. Essentially, these MIs are scrap paper for the controller. They are meaningless to us. They will not be addressed in our program. They are simply used for controller calculations. So now that we've finished up the function block, the configuration function block, the question is, why would we auto-tune? We always recommend auto-tuning because each system has its own individual set of ideal PID values. We have already covered the proportional band, the integral time, and the derivative time earlier in the presentation. These three values will be determined using auto-tune. We can manually find these parameters, but this takes experience as well as time. Many times it's a lot of guess and check, trial and error. And it takes quite a bit of time to get the parameters that we're looking for. It's very nice that AutoTune finds these parameters for us. Essentially, AutoTune learns the system and calculates the optimal parameters. Now we'll talk a little bit about how AutoTune works. AutoTune is going to run on-off cycles, which means that it's going to turn the output on and off, either 0% or 100%. Now this is going to create a wave. The process value is going to overshoot the set point and then drop back down. Based on how the system responds to this type of wave, the PID parameters are calculated. We can run a number of cycles from 1 to 3. The more cycles we run, the more precise the results will be, but the longer the AutoTune process will take. It's worth noting that AutoTune must be done once only, the first time we run our system. Once the AutoTune is run and the PID parameters are found, we never have to run AutoTune again. The parameters will be saved. Now this is a graphical representation of AutoTune. You'll see that the process value overshoots the set point 4 consecutive times. Again, the blue line is the set point, the red line is the process value, and the green line is the control value. the first overshoot is not used for calculations. This is disregarded by the controller. The next 3 overshoots are stages 1, 2, and 3 of the AutoTune process. You'll see at the end of stage 3, PID begins, and the process value tracks the set point. You see the blue line matches up with the red line. Below, you'll see the green line begin to fluctuate. This is the control value, and it's attempting to keep the process value directly on the set point. So it's providing a small amount of heat, or output rather, I should say, to keep the process value from fluctuating. Now, in certain cases, manual tuning is required. The ideal parameters of PID for a system are not always ideal. Some examples of systems that may need manual tuning is a system in which we want the process value to reach the set point as fast as possible. Another example would be as a system that never overshoots the set point, so we never want the process value to overshoot the set point. An extremely smooth curve might need some manual tuning, as well as a dynamic or variable set point. Finally, I want to discuss PID Server. PID Server is the ideal tool for understanding, learning, and debugging a PID process. All the graphs that you've seen in this presentation have been provided to us using PID Server. PID Server lets us view the process value, the control value, the set point, as well as many other variables in graphical format. It's a very useful tool. It can be used to view the process, it can be used to log the process graphically, it can be used to troubleshoot, and it can be used to auto-tune. Now, PID Server is an independent part of VisiLogic. It is also an option in the VisiLogic software. Most importantly, it is free of charge, available on our website. Thank you. Now, I would like to move on to an example of PID. Currently, on my desk, I have a tea kettle filled with water. The tea kettle has a thermocouple placed in the water, and this thermocouple is providing a reading to a controller I have on my desk. I also have a solid-state relay that is turning on and off a heater that is heating the water. So let's talk a little bit about the setup in the VisiLogic software. I'm going to go to my hardware configuration. I'm using a V350 35 TA24. Under analog inputs, I have a type J thermocouple defined in degrees Fahrenheit, and I'm storing this value into MI0. This is going to be my process value for the system. It's going to be my input. Next, we will look at the high-speed outputs. And you will see that I have one high-speed output defined using PWM. This is going to be my heater. The important thing to note here is that the duty cycle is set to MI2. This is going to be our control value, or the PID output. So as we covered in the presentation, in the main routine, We have our power up bit acting as a trigger to the PID configuration function block. I will open up the PID configuration function block, and we're going to review these parameters one more time. We have our set point as MI3. This is a variable on my HMI display so that the user can change the set point. My next variable is the process value for my PID, the input. This is my thermocouple. Next, the proportional band, integral time, and derivative time are going to be calculated using Autotune. We simply assign MIs to these parameters, and they will be updated by the Autotune. Our next variable is our sample time. Again, this is how often the controller calculates the PID. Units of 10 milliseconds. I have assigned 5 for a total of 50 milliseconds. Next, we need to define our action. Again, on my desk I have a tea kettle, and I'm heating the water. So our action is going to be 0. Reverse, heating. If I was attempting to cool the water, we would use 1, direct cooling. This is not the case. We are attempting to heat this water. Next, we're asked for the input range. This is the process value range, the range of the thermocouple that I am currently using. The range of the thermocouple is 50 degrees to 300 degrees. So I've assigned 500 to my low limit with an offset of 1 decimal point, so 50.0. And I've assigned 300 to my high limit, 300.0. Next, we're asked to define the output range. Again, the output range is going to be 0 to 1,000, representing 0 to 100% with a 1 decimal offset. Finally, we have our control value of the PID, which we have linked to the duty cycle of our high-speed output. So our duty cycle, based on the PID calculations, is going to have a value from 0 to 1,000, which again represents 0 to 100% of the duty cycle. Next, we have our PID status defined. This will help us troubleshoot. And we have linked a group of 32 MIs, which again are just scrap paper for the controller. So essentially, in this function block, all that is needed is the set point, the process value, which is the input, a sample time, how often would you like your system to update, the action, heating or cooling, the input range, which is my thermocouple range, the output range, which is 0 to 100%, the control value itself, which in this case is the duty cycle of my high-speed output, and that's all for numerical information that we need to enter. Also, I would like to note that the name of the PID loop can be found here. It can also be changed. For now, we'll leave it as is. So this configuration function block will run on power up. We are then calling the subroutine PID. Let's take a look at what is in the subroutine. Now again, the first thing we want to do with the PID system is run a Autotune. Memory bit 2 is a button on screen that says Autotune. Let's take a look. Run Autotune is my memory bit 2. So when I push Run AutoTune, it's going to ensure that the PID is not already running, which is memory bit 5. It's going to ensure that an AutoTune process is not already running, memory bit 3. It will then set memory bit 3. Memory bit 3 is going to act as a trigger for the PID AutoTune. Here we're checking to make sure that the PID status, memory integer 14, is above 0. If we have a PID status above 0, that is a good thing. It's telling us that our PID is okay, and it's simply giving us the state of the PID. If we have a negative PID status, then there is a problem with the system. So to summarize, we're pushing a button, setting a bit. The bit then acts as the trigger for the AutoTune. This is the AutoTune function block here. It can be found along with the rest of the PID function blocks. Under Function Block drop-down menu, PID AutoTune. Here's the configuration function block, the AutoTune function block, and the Run PID function block. So currently we're talking about the AutoTune. Let's take a look inside. It asks us to select which loop we're working with. We have only defined one loop in this example. If there was more than one, we would have the option here. Next, it's going to ask us for a number of stages for the AutoTune. As mentioned in the presentation, we have the option of 1 to 3 stages. Again, the more stages we run, the more accurate the PID parameters will be. The less stages we run, the faster the AutoTune will complete. Finally, it asks us to link a memory bit for when the PID AutoTune is complete. This bit will go high when the AutoTune has completed. So once the AutoTune is complete, memory bit 4 goes high, and it resets memory bit 3, which resets the AutoTune, stops the AutoTune. Once the AutoTune is complete, we can then push memory bit 4, which is another button on screen. This should say, here's my button on screen, which is linked to memory bit 5. So when we push memory bit 5, it's going to check and make sure the AutoTune is done. It's going to ensure that an AutoTune is not currently in progress. It's going to ensure that our PID status is greater than 0. And then we are going to run the PID. Please do not be fooled by this name, PID AutoTune Run. This is in fact the Run AutoTune function block, and this is the Run PID function block. So please do not be confused by the name. So again, just to summarize the whole process, we're going to push a button on screen. The AutoTune will begin. The AutoTune is going to do 3 total stages in this case. When the AutoTune completes, we will then have the option to run the PID. Now let's take a look at a AutoTune that I completed this morning using PID Server. And as a side note, PID Server is located in the Tools menu, PID Server. So I'm going to open up my AutoTune example from this morning. And here is the AutoTune of my tea kettle on my desk. Before I could run the AutoTune, I must first link the proper operands to the functions. So you'll see my set point is asked for. I can go back to my program, open up my PID configuration function block, and I see my set point is MI3. So I define my set point in PID server as MI3. Next, it asks us for the process value. We can take a look in the PID Autotune configuration, and we see MI0 is the process value. So we link MI0 in PID server. It's important to note that not all of these are in order. The next variable that we are asked to link is the control value. The control value is located here in the PID configuration. MI2. And so MI2 is linked in PID server. You can see here how the AutoTune works. The process value approaches the set point because the control value is currently 100%. Once the process value reaches the set point, the control value drops to 0, and the process value is allowed to cool. Again, this is a 3-stage AutoTune. The first overshoot does not count or is not considered in the calculations. Now from this AutoTune, the controller determined that a value of 333 for proportional band, which is 33.3% of the input range, is ideal for this system. It also determined that the integral time of 121 is ideal, and a derivative time of 272 is ideal. These are not values that I have chosen. These are the values that the controller has come up with after running the PID AutoTune. PID server is very feature-rich. It allows us to view different things graphically. And is a very helpful tool for troubleshooting. Now I will close my AutoTune, and I'm going to open up a blank application that I have for PID server with my parameters already entered. Now currently I have a PID loop running on my desk. Again, I performed the AutoTune this morning. So I can go online and I can view what's currently happening with my PID. And you will begin to see the blue line. And I'll zoom in a little bit. We can see the blue line here is my set point. It's currently set at 150 degrees. And if I get rid of the blue line, you will see the red line, which is the process value, equaling the set point. So my target, my goal, is 150 degrees, shown by the blue line. The red line is tracking the 150 degrees perfectly. We can also see the output here, or the control value, which is very low. It's at 40 right now, which is 4% of the output. So it's providing very little output to keep that process value at the set point. You will see that my proportional band is still 333, integral time 121, and derivative time 272. These were again determined by the AutoTune. You can also see numerically my process value here is 1502, representative of 150.2 degrees. My set point is 150 degrees. Again, I can't stress enough the importance of this tool. It is very feature-rich, and it is very helpful for debugging PID systems. Now, to simulate a little change in the system, I'm going to dump some cold water into the tea kettle. Now, when I dump the cold water into the tea kettle, I'll zoom in. You can immediately see the process value is falling. We will see the control value increasing in an attempt to correct the system and increase that process value so that it once again matches the set point. We can see here graphically the spike in the control value, the output. We see the dip in the process value. Now we are currently trying to get back to the set point. Finally, for those interested, I'd just like to talk a little bit about advanced manual tuning. Now, what I mean by advanced manual tuning, before I go into this, the PID parameters calculated by the AutoTune are shown here. We can manually adjust these three parameters to effectively make the system act different. So a more aggressive proportional control is equal to a smaller proportional band. If we take a smaller percent of the input range and make that our proportional band, we're going to have a more aggressive proportional control. The output is going to stay on longer. More aggressive integral control is a smaller integral time. And again, the integral time is the time that we would like the system to reach the set point. So if we have an integral time of 10, that essentially means that we expect the process value to reach the set point in 10 seconds, which is rather aggressive. You'll notice that my PID AutoTune calculated an integral time of 121 seconds. So it's expecting the process value to reach the set point in 121 seconds. And finally, we have our derivative action. More aggressive derivative action is equal to a larger derivative time. So, if our curve here for the process value is not smooth enough, we can increase the derivative time. And that will smoothen the curve of the process value. Well, that concludes what I had prepared for you today. At this point, I would like to open up the discussion for any questions. Please feel free to enter them now. All right, so we have a few questions. I promise I will get to them all. Our first question is the difference between the Autotune block and the Autotune run block. Now, this is a very common mistake made by even myself. In the PID options, we have a run Autotune block and a run PID block. The run Autotune block is the block you see before you. It asks you for the number of stages and an Autotune done bit. This block is going to perform the Autotune. It's what's going to create the overshoots and undershoots, and it's going to calculate the parameters for your system. The next block is the run PID block. And you'll see the run PID block in the ladder takes the name PID Autotune Run. This is a very deceptive name, and what it actually means is PID Run. There is no need to run an Autotune to run this function block. This simply should say PID Run. So I hope that clarifies the difference between the two function blocks. If it does not, please ask an additional question and I will address. Okay, so our next question is, would zero integral time, mean we can expect instantaneous changes? A zero for integral time actually means that integral control is turned off. There is no integral control when the integral time is zero. The lowest integral time that we can set for an immediate response is 1. Okay, our next question. Would the PID work with load cell? The answer is absolutely. The PID will work with load cell. The load cell would be the input, telling us how much is on the load cell. And the output would be a piston or something along those lines as the output. So yes, the PID will work with a load cell. So the example that I performed was with a high-speed output. This does not always have to be the case. We can use an analog output, which I will go over very briefly. So if we assign an analog output, say a 0 to 10 volt to MI51. In the PID configuration, I know that this output is a 12-bit output. So for my output range, I would have 0 as the low, and 4095 for the max. This is the range of a 12-bit analog output, 0 to 4095. And of course, I would change the control value to MB51, which is my analog output. So now, again, we have a 12-bit analog output that we're controlling here. The range is 0 to 4095, as defined in the specs. And the output is our control value. So we have another question. Would this temperature control work with PI controls only instead of just PID? The answer is yes. It most certainly will work with just PI control. If we wanted to just work with PI control, then our curve would be slightly bumpier. That's all. The derivative acts to smooth out the process value curve. I just want to clarify some confusion. One of the questions was, is there a different application for AutoTune? The answer is no. It's all one application. Here we have the SB2 configuring the configuration block, the PID. And then we have a subroutine, which we're calling constantly, called PID. And the AutoTune is performed in these first two blocks. A button on screen is pushed, and the AutoTune begins. Once the AutoTune is complete, we then have the option to run the PID, which is these two rungs here. Again, we push another button on screen, and the PID run is activated. Again, the AutoTune must be done first. Then the PID run can be done second. AutoTune must only be done once per system. All right, so we have another question. What if we're not doing a heating or cooling application? What do we set for our action? Well, heating, or our action, is not necessarily referring to our heating or cooling. If our process value, our current value, is lower than our set point, which is our target value, then we will be using reverse action. If our process value is above the set point, larger than the set point, and we're trying to reduce the process value, bring it down to the set point, then the action of direct would be used. I hope this clarifies the confusion. If not, please ask another question, and I would be happy to answer. All right, so we have a question regarding AutoTune. I will bring up the AutoTune. Okay. So I think there was some confusion. A few people thought that the AutoTune began at the set point, when the process value reaches the set point. It actually does not. Once we press the AutoTune, the process value, in this case, is about 70 degrees. When we press the AutoTune button, the process value will increase because the heater was turned on, and the AutoTune takes care of everything. There is no need to increase the process value to match the set point before starting AutoTune. Again, the AutoTune is going to take care of the entire process. All right, so we have another question regarding the input range. Somebody pointed out that my input range is 50 degrees to 300 degrees Fahrenheit. However, water cannot be brought to over 212 degrees Fahrenheit. The reason that I'm using 50 and 300 here is because that is the specs of the thermocouple. That is the range of the thermocouple input. These do not have to be 500 and 50 and 300. They can be modified to your system. So we could, in fact, put 212 degrees here. But like I said, the lower and upper limit of this specific thermocouple is 50 to 300, and that's why those values are used. However, you could modify these values to your system. Okay, we have a very good question. Can you dynamically change the action of the PID, i.e., the action here? You can dynamically change anything in this function block. However, you cannot dynamically change the input and the output. So what we would like to do, instead of using all one function block, is use two PID configurations. We'll use one for heating and one for cooling. For example, if you have a heater heating water and you have a fan on the top that you want to cool the water, we can do this and accomplish this in two separate PID configurations, two independent loops. And we do have examples of this, and they will be available shortly after the webinar for anyone who is interested. All right, so one question is, when would we use the pause PID? Pause PID would be used, for example, if we have an oven and we are heating the oven to a set point and someone opens the door of the oven. Immediately, heat is going to exit the enclosure. So what we want to do is pause the PID. We do not want the PID struggling to catch up and to heat the oven as quick as possible because it will never reach the set point with the oven door open. So what we do is we can pause the PID based on an input. Say we have input 5 is oven door. If the oven door is open, we can then pause the calculations. All right, so we have another great question. Let me just rephrase it. All right, so the CVP, CVI, and CVD, are they linked in VisiLogic? And can I show them on PID server? Well, yes, I can. This can be located in rung number 6 of my example program that I will be putting on the web. And I'm using a function block in rung number 6 called read control components. And I will open up the function block that I already have. And we are going to be reading the control components. These are the CVP, CVI, and CVD values. We are asked for a factor of resolution. We give this a power up value of 100 because we want to scale down these values so that we can see them on the PID server. Now let me open up the blank application. So you notice in VisiLogic we are reading the control components into MI48, 49, and 50. These are then linked in the PID server, 48, 49, and 50. If I go online with the controller, I can then view these in the system, in the server. And you'll see the black here stands for CVP. CVI is in pink, which is all the way up here. And CVD is the gray down here. So these values can be linked in the PID server as long as you are reading them in the VisiLogic software. So we have a question for clarification. The question is there an optimum percent of the PV range in which to auto-tune? Now, we have a PV range set already in the configuration function block. The PV range that I'm using is 500 to 3000. Now the auto-tune is going to calculate a percentage of this to use for the proportional band. So the auto-tune is calculating this, and that is not user-defined unless you're manually tuning the system. The auto-tune will adjust based on the input range that you define. Okay, we have another great question. If power is removed from the controller, will the PID parameters remain, as well as the set point, or will we need to run a new auto-tune? Now this has to do with the memory of the controller. All MIs are backed up to the EEPROM. So if your controller loses power, the battery in the controller will retain the values in these operands, and the next time the controller is powered on, the values will remain. The only exception is if the battery in your controller dies. In this case, you will lose the entire application, and you will know when the battery dies. So yes, the PID parameters are maintained, and there is no need to run another auto-tune upon power-up. All right, so we have a question. How many parallel PID loops can VisiLogic handle? If we refer back to our PowerPoint, let me find the slide. Here. With the Enhanced Series controllers, the V130 and above, 24 loops are supported, individual loops. That means that we can have 24 PID configurations, 24 auto-tunes, and 24 run function blocks. In the standard series, 12 loops are supported, and in the Jazz or M91, 4 loops are supported. Okay, so we have another question. How does derivative control affect the process? The derivative control acts to smooth the process value curve. It takes a look at the past curve, and the derivative action attempts to maintain the direction of that curve. So it's going to add or subtract from the control value in an attempt to maintain direction. All right, we have another question. What MIs are used for the PID calculations? The answer is whatever MIs you select. So here we have MI15 selected with a length of 32. If we did not want to use MI15, we could use MI2000. With a length of 32, MI2000 to MI2031 would be used as scrap paper. or calculations for the PID. We just need to reserve these 32 MIs. It doesn't matter where. All right, so we have a question. Assuming we're using a 4 to 20 milliamp output, you can find the high and the low limits in any of our documentation. For example, I know off the top of my head, if you have a 12-bit 4 to 20 analog output, then the output range is 819 to 4095. So yes, the low and the upper limit will be affected, and you always want to check this in the documentation of your controller. All right, so we have a very good question. Let's say we have multiple systems with the same setup. They're all going to be using the same PID setup. Same heater, same temperature probe, same everything. In this case, we do not need to run multiple auto-tunes. We can simply run one auto-tune, retrieve the proportional band, the integral time, and the derivative time values, and we can implement them as power-up values here. So proportional band was 333. I would enter a power-up value of 333 for the proportional band. Assuming we do not have a subroutine, all that is needed is a run function block. So assuming that we already have the proportional band, the integral time, and the derivative time from a previous auto-tune, we can enter them as power-up values and simply run the PID. The auto-tune does not need to be incorporated into your ladder, and it is simple as 2 lines of code. Okay, we have another question, a little bit redundant, but just to clarify, if we already know the proportional band, integral time, and derivative time for our system, there is no need to run a auto-tune. We can simply enter these values as power-up values, have this configuration run on power-up, and we can either start the PID immediately or start it based on some button on screen. All right, so we have a question. Can we view the PID loop in PID server while the controller is functioning? The answer is absolutely. My controller is actually functioning here on my desk currently, and I can go online with PID server, and I can view graphically exactly what's going on with that PID loop. My controller can be running other functions, that's not a problem. As long as I have a connection to the controller, I can view the PID loop in PID server at any moment in time. All right, if anyone has a specific question on their system or the capabilities of our PID with specific systems or setups, please feel free to give us an email at support@unitronics.com, and I would be happy to answer each one individually. So we have an excellent question. Here we have our output range 0 to 1000 representing 0 to 100% for our duty cycle. If we do not want our duty cycle to go above 50%, we could simply change the max output range to 500. In this case, the duty cycle will never be above 50%. Okay, so we have another question. It's regarding the input range. And the question is, if we have a thermocouple, let's say, has a temperature range from minus 100 degrees to positive 5,000, or let's say 500 degrees. Would it be better for the system to decrease this range? Now the answer is that if you're running an AutoTune, the AutoTune's not going to care what range you have. It's still going to base its calculations off of how your system reacts. So if it feels that the best range for this process value high and low limit is, let's say, 10%, and we decrease this range, let's say 0 to 3000, and cut the range in half, then the proportional band will be 20% instead of 10. It's still going to keep that same range. So it's going to base the range off of the range and not a percentage, if that makes sense. All right, we have another great question, and we're getting a little bit into manual tuning now, so it's getting a little bit more advanced. But we have a question: do we have to worry about integral windup? The answer is yes. The integral, it acts as a wind-up feature. So if we're not reaching the set point in the time that we have allotted, the integral error is going to continually build up higher and higher and higher, and so on. If this integral wind-up gets to a certain point, then the output can be running at 100% all the time, no matter what the PID is calculating. To prevent this type of wind-up, we have an error integral function, and we have a read error integral, which is going to tell us how wound up the error integral is, and we have a force error integral. We can force the error integral to 0, or essentially reset it. So depending on your system, you can read the error integral. If the error integral is above a certain number, you can then force it to 0 by resetting it, or force it to another number. All right, so we have a question about the 32 MIs that we must define as scrap paper. It is essential that you do not overwrite these MIs. These MIs are used by the controller, and they cannot be overwritten. If you are, in fact, worrying about overwriting these MIs, you can realize, or you can see, that once you define them, a group is automatically created giving definitions to these 32 MIs. So hopefully, since they have definitions, this will assist you in not overwriting them. But again, it is critical that you cannot overwrite these group of MIs. All right, so that's going to conclude our webinar for the day. If I missed your question, or if you have a question about your specific system, please feel free to send an email to support@unitronics.com. Myself or one of my colleagues would be happy to answer any questions you have about your PID system, functionality, capabilities, anything that you might have. This webinar, along with the program and PID server that I showed, will be available online shortly after the webinar is complete. The webinars can be found in our support page, Unitronics.com. Apologies. Unitronics.com. Go to the support page, and then webinars. Here's a list of all the webinars that we have completed. PID will be added shortly. And again, if you have any other questions, please feel free to direct them to support@unitronics.com. Thank you for your attention, and have a great day.